Okay, so we considered a case where the input is a weighted summation of two complex exponentials at two different frequencies, and we saw that when we pass this input through our LSI system, whose impulse response is h of n, we get an output which looks a lot like the input, except that there is an additional weighting that each individual component, x1 and x2, they experience, and the weighting that they experience is determined by this function h, capital H, big H, evaluated at the location of that particular complex exponential, f1 for x1, and the x2 of n is rotating at frequency f2, and so it experiences a weighting which is capital H. Remember, capital H is that polynomial evaluation at frequency f2, uh, which is what is written over here. So we have seen that the output is now sum of x1 and x2, except this signals are additionally weighted by h of f1 and h of f2. So now let us generalize this further. Why to stop at only two inputs? And x of n is comprised of two different complex exponentials. We just make it a summation of some arbitrary number of complex exponentials, each rotating at some unique frequency, and each having a unique uh, weighting, which is denoted by this capital X number. And so it will not be hard for you to realize that the answer that we are going to get is going to look pretty much like this, except instead of just two terms, now we will have more number of terms. So that is what we have done in this slide, where we have said that we will let x of n to be a generalized summation over this index k. Remember, n here, small n, represents the index of the time. As the time progresses, n increments. Whereas this small k is now indexing our frequencies. So k is the index of the frequency now. And so f of k is the frequency, is the kth frequency in this summation, and capital X of k, capital X of small k, is the weighting of that complex exponential phasor uh, that we have used. Now, before we proceed further, basically we are going to pass this x of n through our LSI system and then see what the output is. And that derivation is going to be simply a repeat of what we did on the prior slide. And so the answer is not going to be too surprising for you. But before we do that, let us look at this equation over here. In fact, this is quite an interesting equation, because what it tells us is that if all that we know is the values of x of k and f of k, then using this equation we can generate x of n. In other words, we can synthesize our time domain sequence x of n using capital X of k and f of k. So why is this useful? Well, it can be that this time domain sequence is very large. Maybe it goes on for several hours or several days. It can be some discrete time sequence that, for example, seismologists, people who are looking at the measurement of earthquakes, maybe they are looking at that. Or it can be some electromagnetic radiation that is being received from the outer sky, and people are wanting to know whether that is coming from some type of black hole or some type of distant star. And so again, they want to measure the data over a long duration of time. And so there will be simply far too many samples of x of n that are being collected. So one possibility is that we record each individual value of x of n, But the other possibility is that maybe if we represent x of n like this, maybe there are not far too many frequencies present in this discrete time sequence x of n. Maybe the summation over k is only maybe 10 or 15 terms, or maybe even less. Then in that case, if we are allowed to store only those 10 or 15 numbers, x of k and f of k, then you can see that we have to store much less amount of data. In fact, we have done data compression. So this is a methodology. This allows us a methodology for data compression that actually we have talked about earlier in the semester. If you go back and look at the notes of some lecture sessions that we had on data compression, you will actually see that this was one of the techniques that we had mentioned for algorithmic data compression, not the probabilistic data compression, which was focusing on Huffman coding or Lempel-Ziv coding. But remember that we also said that there is an algorithmic method of data compression. So this allows us to do that, this equation. This equation is essentially called the synthesis equation. Why? Because we are synthesizing our DT sequence using this equation. And so now we just extend our earlier calculations, and we see that now the output is just the weighted summation of the complex exponentials, except the weight which was just x of k before, meaning the weight of complex exponential at frequency f of k. At the input it was x of k, capital X of k. At the output, that weight has changed from x of k to h of f of k times x of k. What is h of f of k? It is this capital H polynomial evaluated at frequency f of k. Okay, so now let us formalize this and maybe describe what we have done so far and give it the name that it is widely known as. All of these equations, we haven't named them, so that is what we are going to do. And the name, as you may have guessed, is that we are going to now start using is oh yeah, so okay, before we give this particular operation a name, let us generalize this further. What we have done is for the discrete time sequence, obviously it generalizes to the continuous time signals. Remember, in discrete time we have sequences. When we move to continuous time, it becomes signals. It's just the nomenclature that we are using. The input sequence x of n, which we have taken it to be of this form, remember, using that synthesis formula. How will it generalize when we go to CT? Well, first of all, this summation will get replaced by integration. And then this x of capital X of k, because it is indexed by the frequency variable, it actually will become a function of frequency. And then finally, whenever we have integration, we need to have that delta, infinitesimally small delta term. But that delta term will now be nothing but delta of frequency. And so this equation generalizes to a continuous signal x of t given as this. Capital X of k became capital X of f. E to the power j 2 pi fkn became just e to the power j 2 pi ft. F of k became this variable f. N became t. And because this is f of k, and now we have made it continuous in frequency, therefore we have this d of f term. basically this summation became this integral. And this you have seen in your high school calculus, that the integration is just the limit form of summation. So that is all we have done here. Let us give it some name, equation A, because we will be referring to this equation later on. Now remember the sequence at the output y of n, we have written it as convolution of x of n with h of n, and that from the previous slide had this particular expression. And so when we convert this to continuous time, again this summation will get replaced by the integral sign. There will be d of f term here. But x of k and h of f of k, they will now turn into simply x of f and h of f. And so this is the continuous time signal at the output of the linear time invariant system, LTI. Okay, so now is when we get into our nomenclature. What we have done now is actually we have defined Fourier transformation. You see, we started out with convolution operation. We looked at the formula for the convolution, and we saw what it means by looking at it from linear algebraic viewpoints. We looked at several applications of convolution. We started this entire topic by looking at the third kind of theoretical application of convolution, in which we talked about the multiplication of just some two numbers, and we saw that even in our elementary school, when we were multiplying the numbers, we were actually doing convolution. But more importantly, we said that that particular viewpoint of convolution leads us to the eigenfunction or the eigenvectors of the LSI or LTI systems. And when we understand what is going on when we apply the eigenfunctions at the input to the LTI, we ended up with several expressions which were on the previous slide. Now those expressions are nothing but Fourier transformations. So convolution has actually led us to this elegant theory of Fourier transformation, as we will summarize it over here. So the Fourier transformation of a discrete time sequence h of n is defined as simply this capital H of f. This is the terminology that we had on prior several slides. Now, on this slide, we'll bring one more viewpoint of this. That if you think of this H as being a vector, then we can convert this exponential phasor term also into a vector. And the only parameter that it is dependent on is this frequency f. Remember, this m is just index in time, or it is the index of the element of the vector. And so this summation can be represented by this dot product. The dot product I have denoted by this small circle. So this is a view of looking at capital H of f. It is the Fourier transform of the dt sequence, and it can be thought of as the dot product between vector h and complex conjugate of vector e of f. Essentially, we are projecting our vector h onto this vector e of f, and it may turn out that h is highly aligned with e of f, in which case this projection, the dot product, will become pretty high. Remember, dot product measures the alignment between two vectors, because it is proportional to cosine of the angle theta between the two vectors. And so whenever that alignment is high, we will get pretty high value of capital H of f. Whenever this vector h and this vector e of f conjugate, by the way, this term here in Superscript doesn't denote convolution, it denotes complex conjugation. The same symbol, but when used in a different context, it means a completely different thing. So when this H vector and E of F vector, when they are perpendicular to each other, then capital H of F will become 0. So this is the Fourier transformation of a discrete time sequence. And so obviously it will generalize based on the formulas that we had on the prior slide. It will generalize to this expression here. This M became T, and then we needed to put this d of t terminology, and the summation became the integral sign. And this is nothing but the continuous time Fourier transform of a signal h of t. And just like what we did here, we can think of this as if this continuous time vector h of t is getting projected on this complex exponential phasor rotating at negative f frequency. Essentially, when we measure this capital H of f, we are projecting h of t on this exponential e to the power minus j2 pi f t, and we are seeing how much strength we get through that projection. That projection strength is our h of f. The other way to think of this is that it is as if we are trying to find out the strength of the frequency f which is present in h of t. If frequency f is not present at all in h of t, then these two vectors will be perpendicular and we'll get 0 as the answer. Okay. So maybe let us stop here, and we will resume this topic in the next lecture.